By now, you've probably heard about blockchains and how they're driving banks, venture capitalists, and crypto-libertarians into a frenzy. Maybe you've seen explainer videos with stacks of blocks or sci-fi spiderwebs overtaking the planet, but just forget about all that for a second. The important thing to remember about blockchains is that they make it harder for digital data to go rogue. Digital information likes to be free. Just ask the recording industry. Once a file is created, it can be copied, modified, and quickly develop a wild social life all its own. And before you know it, you're looking at a photo of kitties on the moon. Digital data's libertine tendencies encourage companies to hoard it. It's why the simple idea of digital currency took a long time to figure out. Blockchains are promising because they can make data you can trust. The trick is to bind that data into a strict framework of rules using cryptography. A blockchain creates a kind of shared record or database, with each piece of data secured with its own cryptographic keys. Only people with the right digital keys can add data to the blockchain, or modify information that's already there. You can get the upside of the internet, like speed and transparency, without the downsides, like rogue data. Digital currencies, like Bitcoin, use blockchains to prevent counterfeiting. And because computers belonging to many different people enforce the rules, no one is in charge and there's no need for a central bank. Companies can use blockchains to create a safe space to share data and collaborate with competitors. That could mean faster and more transparent financial transactions, less identity theft, and easier ways to share your medical records. Some food companies are even using blockchains to be more transparent about their supply chains, which could help avoid outbreaks of foodborne illness. I'll be honest with you, a lot of blockchain's applications can sound kind of boring. They're about making accountants happy by making things a lot more efficient. But some use cases are more radical. Digital currencies are being tested as a way to help people not served by conventional banks, like refugees. The gemstone industry is testing a blockchain to prevent sales of blood diamonds. Blockchains might even make it possible to safely allow people to vote over the internet. So those are blockchains, digital data you can actually trust. And remember, don't worry about the block.
GIS software history is about our users and developers are fighting against the ever-expanding geospatial data. From the classic survey data to a new generation of serving data, like BIM data, point cloud data, and to geospatial big data, like cell phone data or IoT data. So with those large amount of data, it brings big challenges for our traditional GIS software. Just do a simple overlay analysis. The time consumption will reach 10 hours if we did the analysis with 100 million records. And also, what's worse, the traditional GIS software cannot deal with those big data. With this large amount of data, what should we do? If we manage and store them distributedly and also do analysis and processing them in multiple machines at the same time, we will have a much higher working efficiency. It's how distributed technology works. To transform our GIS software to distributed ones, we have to transform it from data management and storage to data processing and analysis and to data publish. And also, don't forget our infrastructures like our cloud centers and servers. Firstly, let's look at distributed geospatial data engine technology. In the past, we always use relational database like Oracle or MySQL to manage 2D geospatial data. But those relational databases cannot handle 3D data and big data. With those distributed databases, it's easy to manage those data. So we built up a distributed data engines. It includes distributed file system, distributed SQL databases, and NoSQL databases. With the distributed data engine, we could quickly do any data uploading and data query. Here's a case of millions of land use data managed in HBase. It only takes seconds for data query and search. The other example of is a global flight demonstration demo based on Supermap distributed GIS and Alibaba PolarDB. In this demo, it has billions of global flights data. We could also quickly do any search and query, and it will quickly visualize the global flights data. And distributed technology also help us solve the 3D data rendering problems. Through input those multi-source 3D data to MongoDB, we could rendering and visualize 3D data very soon. Here is an example of 500 square kilometers of manual modeling data. We could, it reaches on a second's response time to visualize, to rendering and visualize it. In this case, it's a 3.2 trillion bytes oblique photogeometry modeling data. The rendering and visualization efficiency is also very fast. So now we solve the data management problems. Our final purpose is to do the data mining to solve the real world problems. So it's time to go to our second part, distributed geospatial analysis and processing technology. What is distributed geospatial analysis and processing? We split those single complex tasks into multiple subtasks and do collaborative computing with multiple machines. Just imagine multiple machines working at the same time will be much faster than a single machine. We also did a test. Here is a 44 million land use records. We did a regional summary. With the traditional standalone method, it takes 14.5 hours. But with distributed computing model, it takes only 22 minutes, which has a 40 times performance increase. For the raster data, we did a statistics of global cropland. The traditional standalone method takes a day and a half to finish the whole statistics, but the distributed method only takes 44 minutes, which has a 50 times performance increase. So to transform our traditional operators to distributed operators, we have to change them from classic geospatial data analysis and processing, geospatial big data analysis, and geo-AI algorithm. With those distributed operators, we could do like overlay analysis like we did in our traditional GIS software. This is for a land use data, and also do a slope analysis for 3D terrain data. Still, we could use big data to do analysis like hotspots analysis or streaming data analysis to monitor the city's operating conditions in real time. With AI algorithm, we could predict housing price with variables like transportation, education, medical conditions, and so on. To help us to do any housing research or to do any investment decisions. And recently, the distributed computing also supported by the geoprocessing modeler. In this geoprocessing modeler, we could build up very complex model to do any spatial analysis. And with the distributed computing, the working efficiency will be very fast. So now it seems that we have a much powerful GIS software, but here's one problem: is the stable. It's a system stable question. Can we keep the system stable as always? Now we have to use the cloud-native GIS technology to keep the GIS software stable and always have high performance. Let's look back to our IT history. From large computer, PC, client and server architecture, virtual machine, cloud computing, our hardware and software improved a lot. And in 2020s, it's the time for cloud native improves our IT technologies. But what is cloud native? It's about a bunch of loosely coupling microservices running in containers. And it realized automatic orchestration with some container management tools like Kubernetes. The cloud-native technology empowers us to build up very scalable applications in public, private, or hybrid clouds, and help us create a better cloud computing world. Applying the cloud-native into our GIS software, we turned our old monolithic modules of GIS software to microservices and packaged those microservices into containers, and then deploy those containers into different machines. And SuperMap provides us a manager for Kubernetes to help us to learn how microservices works. Like those nodes are microservices. Those microservices could auto scaling up and down while data volumes change. Or once one microservice was broken, it will soon be isolated and then will be recovered later by itself. With the cloud-native technology, we did a transformation for a state-level geological big data platform. In this platform, it managed 400 trillion bytes data, and with more than 400 service instances working at the same time. Before the transformation, the platform was based on an infrastructure as a service virtual machine, and the GIS service is on its application level. But after the transformation, we put this GIS applications to a GIS platform based on Kubernetes, and use those GIS microservices to keep the system works very well. After the transformation, the system was never fell down. This is how cloud native help us keep the system always have a high performance. And also, there's still one problem is that if the cloud center have lots of requests from users, it will bring a lot of pressures for the center, and users will have a very slow responding time. How should we solve this problem? So this is this is the Edge GIS technology help us to solve these problems. As we all know, octopus is very magical creatures with 40% neurons in its head and others 60 in its legs. So its legs not only can touch, but also can think. Not like our human. After we touch things with our hand, we have to send this information to our brain and then make decisions. This process will take time, but the octopus, it can touch. It can quickly react after it touches the outside world. If we apply this workflow to our GIS software, like its brain is like our cloud center. If users directly send requests to the cloud center, sometimes when it may because of network issues or some visit volume issues, it will have a high latency. But if we put some legs, which are those edge servers across the close to the user side, the responding time will be shorter. This is how edge servers work. The edge servers and cloud centers work together to satisfy every user's request and keeps the system have a high working efficiency. With the edge GIS servers, we could not only do service aggregation, but also do data delivery and analysis and processing. We could do anything we can in GIS software. Here is an examples of 3D data delivery. With those edge servers, users could quickly load those terrain tiles or S3M tiles or image tiles very soon. So now it seems that our GIS system is very powerful and stable, but here's one thing we didn't mention, which is data credibility. How could we protect our spatial data safe? Nowadays, the blockchain technology gives us an answer. And what is blockchain? The blockchain is designed to be decentralized and distributed into multiple machines. Here's the workflow of blockchain. In blockchain, the data was split into several blocks. In each block, there has a hash code, which is irreversible and has a fixed length character. And each of these blocks connect each other to form a blockchain. And what's interesting is that those hash codes are mislocated stored. Like in the block 7, the hash code is for the block 6. And in block 8, the hash code is for the block 7. So once, if a certain block is tampered, say the data 7 was modified, and then the hash code 7 will be modified too, and the following will be will be changed. And also in blockchain, every data was rapidly stored in distributed nodes. If anyone want to do malicious modification, all the subsequent blocks and related blocks copied on other distributed nodes must be modified. So it's impossible to do any malicious modification. From here, we could conclude 3 features of blockchain, which are safety, traceability, and credibility. If we apply those features to our GIS world, we will form a Geo-Blockchain to help us keep the geospatial data safety. But here are still some tips. As we all know, blockchain is a very complex storage method. It will cause the system performance degradation and also occupies a lot of storage space. But as we all know, spatial data always have a large amount. At this condition, we have what we do is to only upload those K data to the chain. Okay, so here comes up 2 solutions for geospatial data upload to the chain. The first one is direct upload for small data size. If we have a large data size, we could upload those data to external storage, external database, and it will generate a hash code. We only have to upload those hash code to the chain, and it keeps our data safe. In the SuperMap 10i 2020 version of iDesktop X, it provides a blockchain data management tool. Here, users could create, add, and modify any spatial features and store their data on the blockchain. In terms of the applications in the real world, here is an example of food traceability. With the Geo-Blockchain, we could record every detailed information, like where and when the food was delivered, and also the detailed arrival time and left time. So once the food has any problems, we could soon locate where and when the problems might happen. In the cadastral parcel management, the Geo-Blockchain could record every change of the parcels, including their ownership and their boundaries, and so on. It helps us to manage those parcels very efficiently. For other fields, like in planning fields, we could use Geo-Blockchain to do spatial planning and land use control or real estate transactions. For other fields, we could use it for food and pharmaceutical supervision and traceability, logistic location management of important items. The exploration of Geo-Blockchain just start. In the future, there will be more and more Geo-Blockchain applications in our world. So finally, let's make a summary of our today's distributed GIS technology. It includes distributed geospatial data engine, Geo-Blockchain technology. These two are for data management and storage. And distributed geospatial analysis and processing technology to help us have a high efficiency data analysis. And together with cognitive GIS technology and edge technology to help us help maintain the system stable and high efficiency. Those five technology work together to support our GIS software to work very well, from components, desktop, web, and to mobile. Additionally, distributed GIS is one of the key fundamental technology for Supermap.